Let's start. Welcome to the last session before lunch break. And if we miss lunch, it wasn't me. You noticed. So I want to talk about, actually the depth of that talk fits to the level of oxygen in the room, so don't worry. It will not be too much information. I did some kind of fun project and I want to report about that, things that I learned during, something I did just for fun, for the fun of it. So the title is Gaining Skills by Gorging Gas, so you might imagine what I'm doing. And there's also a subtitle which is Why My Son Can Keep His Girlfriend. And you will understand later where this is coming from. So I want to show you 4 different things, why I did all of that, how I did it, what kind of technologies did I use, what are the insights from that, if there are any, and more importantly, and this was the real reason for doing that, what did I learn from all of that? Okay, so the use case. A few years ago, I started learning about machine learning. And the advice was always, do your own project, do something with machine learning, look for your own data. All of the test cases and tutorials were always using ready data sets. The length of petal flowers, I don't know, were really boring. And if you do one of these ready-made tests, then of course the result will be perfect. But this is like building Lego. You know the result will be perfect. I wanted to learn something from my own project. So I wanted to use real data and new data that I collect myself. And of course I want to do everything with MySQL. So as much as possible should run inside of MySQL, just for loyalty reasons. And I want to use as many features of MySQL as possible. So whatever is possible, I want to use it all. There is a famous saying in German, it's from Kurt Tucholsky, detours increase the knowledge of the area. So the more you get lost on your way, the more you learn about the area. And that's why I said, I will not do any optimizations, I do whatever is possible. And I want to use whatever is available. Maintainability of my code is not important. So that's how I don't care for simplicity. I want it as complex as possible to use whatever is available. And maybe I even get something useful out of it. Let's see. But the important thing is I want to learn. So my use case is I predict the gas consumption in our house. We have gas-based heating. And I want to predict the gas consumption based on the important factors. So I identified what are the important factors, outside temperature, obviously, but also who is at home. So if more people are at home, we consume more hot water, so more gas consumption should be relevant. And also we added a fireplace to our house just a year ago. All of that happened a year ago. I started a year ago. And I wanted to see how much does that fireplace contribute to saving on gas consumption. So I also wanted to monitor that fireplace. So I took a Raspberry Pi and built that wonderful machine on our gas meter to take a photo every 5 minutes from the gas meter. That's not the smartest way of measuring your gas consumption, but I was not looking for the smartest way, I was looking for the most fun way. So this is the kind of photos I'm taking every 5 minutes for over a year now. It's a little distorted, but okay. So I have the gas metering, but who is at home? How to recognize who is at home? I checked my Wi-Fi router, the wireless router, and I can check which devices are logged into the local network. And luckily, all of the phones typically have a name like iPhone from Mario. So I know if the iPhone from Mario is logged in, Mario is at home. Mario, that's me. And that's what I did. Every 5 minutes, I have that Raspberry Pi taking the pictures is also running another cron job, taking a snapshot of the logged-in devices every 5 minutes. And then I'm storing everything in, oh no, first, this is disgusting. This is measuring the activity of the fireplace. And I'm doing that manually. So whenever I heat that thing, I take note. And unfortunately, the heat takes very long for that thing to cool down. So all of the second dates, when was it cooled down, are just wild guesses because I was long asleep at that time. So that data is only mildly accurate. I have a work log that says install a thermometer to the chimney and assess this automatically, but not yet implemented. So with all that data, I collected that and I moved that to the Oracle clouds. I used one of these always free instances in Oracle Cloud. So you can use that MySQL HeatWave instance with just one virtual core and run MySQL HeatWave and do anything on that. It's for free, and you have, I think, 50 gigabyte of storage on object storage. That's good enough for me. 50 gigabyte, that should be good enough for many years to come. So all of you can do the same at home if you have a fireplace. And then I loaded everything into MySQL. You see the object storage, a virtual machine that is loading the data, cron jobs, and then the rest is in MySQL. This is the data structure in MySQL. I'm not sure if I'm proud of that data structure, but I'm really proud of that image, actually, and how it moved. This was really important for me, not because I intended to do this presentation here. It is important for me to know what is happening. There were always times, 2 months, where I did nothing on that project. And coming back after 2 months means I forgot everything. I found tables where I said, which idiot created that table? Only one option, it was me. So with that overview, it's really useful to understand what is happening and what do I have everywhere. So this is the overall picture of the data architecture, and to simplify it, I can give you this view. The tables on the top record who is at home. There are some views and some post-processing. What's the weather like? That's very easy. I didn't mention in the beginning, there is a public service from Deutsche Wetterdienst, DWD. They offer downloads for the hourly data for the temperature and humidity for some major cities. Luckily, I live in Berlin, so Berlin is one of these cities. How much gas do we consume? This is where the pictures get in from my photographs, and I do some machine learning to do the meter reading. And does the fireplace burn? This is the table that I fill in manually, unfortunately. Then data consolidation, joining all of these 4 data streams, and then the analytics, who is causing the consumption. So the model of our gas consumption, the machine learning model for that. So what technologies did I use? I will not dig into detail. I would love to, but we have a lunch break ahead, so let's not do that. Just some very broad overview. This is the machine learning pipeline for the OCR, for the character recognition, for the digit recognition. It should be called ODR, optical digit recognition, but I'm not sure. I guess I'm the first person to ever use that term. So let's stick with OCR. I'm loading the individual digits. I will explain that later. And then at the end, I have the actual meter readings. I have another machine learning pipeline on the right-hand side. This is where I have all of the input data, and I create a model to predict the gas consumption. I will talk about the machine learning part in a bit. Then I have JSON data, because the data that comes from my wireless router is actually a JSON document. So I load that into MySQL, and I have some JSON management to convert that into a relational table. At the moment, I'm using a stored procedure that is using JSON table, but what I'm really looking forward to is doing JSON duality views, which we have in MySQL. And JSON duality view means you have two relational tables with a 1-to-n relationship, foreign key relationship, and you create a view that is creating a 2-column table with an ID and a JSON document, and that JSON document includes the outer data and typically an array of the inner data of the n side of the relationship. So you create a JSON document from that, customers with orders, for example. And then you can insert into that view, and the data is automatically distributed to the underlying relational tables. So I would create that JSON duality view, just paste my JSON coming from the router into that view, and the data is automatically converted to relational data and stored in the two tables that are related to that. That would be really cool. But unfortunately today, these JSON duality views require that the subtable has one attribute, which is a primary key. And my router does not provide a primary key on the individual, devices. So I need an auto-increment for that. And today we do not accept auto-increments for the JSON duality views. I have to wait. It is an open workload, not mine, luckily. It is an open workload, we are working on that, and once we have that the sub-relation or the sub-table can work with an auto-increment, I will convert my application to JSON duality views. What else? REST API. I haven't used REST API so far. It would be nice. Currently I'm storing everything in files, and then I have a cron job that is loading these files. Actually, my Raspberry Pi could send the data directly, connect to MySQL to a REST interface and just store the data. That's what I want to do, but it's on my list. What else do I have? A trigger. Trigger is boring. I mean, we have triggers forever. But the interesting thing here, this is a lot of time series data that I'm working on here, right? And I use the trigger for something interesting. I'm polling the devices every 5 minutes, but no one is leaving the house at that rate. So most of the time the state does not change. And I was afraid of storing the state every 5 minutes, so I want to store only events. Someone is leaving, someone is coming to the house. And for that I use the trigger. So whenever I insert Mario is at home, and 5 minutes later Mario is at home, my trigger code is checking before insert what is the last state of that person, or of that MAC address actually. And if the last state is the same as now, I will just not insert that row. So I raise an SQL error, that's my own personal SQL error with no state change, row ignored. And then I can do inserts, and if there is no state change, that insert is just ignored. And if there is a state change, I will have my insert. That's nice to reduce the data volume. It's a bit challenging because you need to do the inserts in correct time order. Otherwise, everything is messed up. And the craziest thing, at the end, I needed the presence data again in an hourly format. So who was present from 6 to 7? Who was present from 7 to 8? So I needed exactly that equidistance time measurements again, not the event-based data. So I have another part of my application that is converting the event-based table into the continuous data stream who is available. And you can do this with a recursive common table expression, for example. So with a recursive CTE, that's the one on top, I create buckets, 6 to 7, 7 to 8, 8 to 9, 9 to 10, and so on. And I join this with my events table. This is here we join with the events and the date CTE. And the join condition is, and that's why it's interesting, the join condition typically is always A equals B. But here I have a join condition with a relationship. So where the when UTC field is lower than the bis is the German word for when. the until field. And when is smaller than this, and until is higher than von, so the start of the bucket. So not the typical join relationship of equality, but with the greater than relationship. And so I converted the data from a 5-minute interval to events-based, and with that query I converted everything back. As I said, detours help to gain more knowledge. Something else in that query is interesting. I had to change the max recursion depth for that recursive common table expression, because I needed more than, I think the default is 1000, so I set it to 2000. Actually, I should have set this dynamically to it's easy to predict how many buckets I need in my store procedure. That's something I can do later on. But these optimizer hints are relatively new in MySQL, so I was happy to use these as well. And what you see here, actually all of that, the stored procedure is in JavaScript. It's not the typical SQL stored procedure, but the stored procedure in JavaScript. So JavaScript is nice because you can create the statement by concatenating variables. That's very easy. You can do dynamically just have a parameter that is giving you the table name that you want to operate on in your stored procedure. And then you do session run SQL statement with your statement string. That's very nice. But there is an even more interesting case for stored procedures that I used over there. When I create different models, I want to document, if I create a model for the guest prediction, I create a view that defines what data is used, which features do I use for that model. And when I create that model, I want to document how I got that data. So I want the show create view statement documented in a table with the results of my model. And only in JavaScript I was able to put the output of show create view into a table. First into a variable and then store it in a table. If you do this with SQL stored procedures, I found no, I'm not aware of any way how you can store the result of a show statement in a variable and then store it in a subsequent insert statement. So that was nice. It's very easy here in JavaScript. What else did I use? Oh, check constraints. Okay, that's a bit boring, but they were very useful for the manual entry of the fireplace. So, because if you enter things manually, it's easy to do mistakes. So I had some check constraints that the dates that I entered are sensible. Okay, let's dig a little bit into that machine learning part, the machine learning for the OCR. You see, I have this photo and I just cut out the individual digits. That's very simple. That's a very simple Python code that I do before storing it in the database. So what I store in the database is actually this bitmap of 96 features. It's a 12:8 image of, this is a binary image. It's just dots and asterisks. What I'm storing is the actual byte value, so it's a full byte for the grayscale of that pixel. So every photo is converted into 8 of these digits, and I store the 96 features, pixels, in a table called digits. And these 96 features is what I use for training the machine learning model. And there's also a training signal. This should be a 2. I hope you can recognize the 2. This was one of the nicer images. You see the problems here already. I have ugly reflections here which destroy things. Sometimes the reader is just in between 2 numbers. There's a lot of reasons why this can go wrong. You also see that distortion. So a 5 on that digit looks quite different than a 5 on this digit or on that digit. Well, I might not live anymore when this is going to 5. But actually, the recommendation is with OCR applications, make sure you have very good input data. This is not very good input data. I should have done much more on the image preparation, but I didn't. That was not my intention. Then I did machine learning the manual way, because I wanted to learn machine learning. I did this in Python. I powered up some notebook, some Jupyter notebook, and then I connected to the database, and then you load the data into NumPy. That's the library to store the data typically. You split the train and the test data set, and then you pick the right algorithm. In my case, Google said it's best to do convolutional neural networks for that. So I did the CNN. And then you have to define that CNN. What is the size? So you need different layers. What is the shape of individual layers? How many neurons in each layer? That's where the black magic starts, actually. But I picked something and then I played with the data. And then you do a lot of experiments with different training set sizes to find the optimum. What is the best training set size? Then you tune the next hyperparameter, which is maybe the size of the individual layers, or the batch size, or there's a ton of parameters that you have to tune, or that you can tune. And it's a bit difficult to know what is the right one. Either you use alcohol, I don't know if that works, or you do a lot of experiments. Or you lose interest one day and you stop and say, okay, the model that I have now is good enough. And that's what I did. After 1 week of doing a lot of Python and machine learning, I created a model with an accuracy of 99.1% accuracy. That's good. I was happy. It's actually not good. It means that every reading has 8 digits, so roughly 8% of all readings are wrong. But first 99% was convincing to me. Then I tried the same in the AutoML inside of MySQL HeatWave, the machine learning. And literally, I'm not making a great case here. It was really that way. It is that one, it's 2 calls. You have to create a table where you put your data. We cannot run machine learning from a view, so you have to copy that into a table. And then it's that one call to sys.ml train. What is the table with the training data? What is the value you're looking for? The task is a classification. There are 10 classes, 0 to 9 for the digits. Optimization metric is accuracy. There are others available. And I want to exclude the columns digit and file name. And that's it. And then I waited for 30 minutes because that always free instance is running on one virtual core. And after 30 minutes, I got a model with an accuracy of 99.1%, exactly the same accuracy that I achieved with 1 word of Python. Okay, I'm neither a Python developer nor a data scientist. That's why it took me a week. And this took me 30 minutes while I had lunch, and I got the same result, the same accuracy. So for these plain tasks, this is really an excellent way to create machine learning models without understanding all of these dirty details, without all of that hassle of optimizing and tuning hyperparameters and so on. So I achieved the same. By the way, on a decent machine, 16 cores, I did the same with MySQL AI, the on-prem version that also includes machine learning. This was running on a 16-core machine, and then it took 2 minutes, that training session. So really impressive, and only inside of MySQL, which was my objective, right? No Python code outside. What is important with machine learning, what I learned, understand your data, know your data. So if I have 8% wrong meter readings, that's not so good. How to identify the wrong meter readings? And I know my data because it has one important feature. The meter readings must always increase. They are monotonically increasing. And if I have 2 meter readings next to each other with a next timestamp, and the gas meter reading is lower than the one before, something is wrong. I have an error in my meter reading. And even if it's much higher, the next one will be lower. So I find that error nevertheless. So with all the predicted digits, I reconstruct the, Zählerstand is German again, that's the meter reading prediction. And from that, I create a view where I have the consistency of the Zählerstand, of the meter reading. Whenever a meter reading is lower than its predecessor, then it ends up in this view. That's a nice windowing function. So with these errors, with these timestamps where I have wrong meter readings, I can then go back and enter more learning data. And this happens, unfortunately, whenever one of the higher digits turns, and for the first time my model sees a 4 on the 3rd most important digit. So then I get errors again. I show these in the, see these in the consistency view, and then I add 10 more training labels for these new labels, for these new meter readings, retrain the model, and then it works perfectly again.
A question now.
Sure.
I guess when you get a result, you always get the most probable one, right? I mean,
yes,
the most probable reading. But there should be like a second and a third and a fourth. There's no way to sort of understand that, okay, I shouldn't pick the first one because it's a lower number, I'll pick the second or third because that's actually consistent with the, already when you get the result, that it can go down and pick a more reasonable value because you understand it.
Yes, that would be possible. So you have, in that prediction table, top right, you have the input data, and then it gives you detailed information with 90% probability this is a 7, and with another 5% probability this is a 1, and the rest. So I could go into that data. Yeah. It was just too difficult for me. Yeah. That's why I didn't do it. I could, for example, see if these correlate with the probability, and if the probability is below 80%, then something is weird already. That would be interesting to do. Yeah. So, what did I learn from all of that? The first, this is the gas consumption over the last year. And what a surprise, in summer we don't consume a lot of gas. It's not a big learning, but here's a gap. And that was a big learning for me. The Raspberry Pi stores everything on SD cards. And these SD cards have a limited capacity. And if you don't want to throw away your pictures because you never know if everything is working well, you end up with the out of disk capacity, and then everything stopped. And I was just lucky to find this after just 1 week, because after 1 week I was going into that system and doing an next training, and I thought, why doesn't it use data from last week? And then I found the Raspberry Pi is there. So monitoring is quite important. And I mean, I'm telling these customers for the last 20 years how important monitoring is. That the shoemaker's kid go barefoot, I think it's the same. Yeah? So just talking about it is something else than really experiencing it yourself. Then about my models that I created. This is the data about the gas prediction models. So the gas prediction models, I did several of these. They differ in the feature set, for example. For every day, or I have some models that are based on 1 hourly data. Some models, most models are based on 24 on daily data. And what I found is that 1 hour is way too fine-grained to do proper analysis. So you see the relative error is plus minus 50%. So the prediction of the gas consumption of the hour 6 to 7 is really yeah, it works. It's better than the base model, which has plus minus 100%. That's just estimating the average consumption for every hour, but it's still bad. But what is quite good is the daily consumption, and what is also important in these features is the temperature of the last 5 days. So I found that the temperature of the last 5 days is important to determine today's gas consumption, because our house is storing a lot of energy, and it's not cooling, it's not losing energy quickly. So the best model was, I think it was gas 12. This is a bit frightening. If the relative error is 0 on the training set, it means it almost memorized all of your training data. So it might be a bad model. But still, also the test error is pretty low. It's just 16%. So the daily gas consumption is plus or minus 16% on average deviation. So that model was the best that I have so far. And with that, this is the graph of that model, so it looks quite good. No wonder, it's only 365 data points, so 80% of that is my training set. And these were memorized. Of course, it looks good. I need a few more years. And then the most important thing with that model, I did what-if analysis. So what if base is the actual thing? So with the real data, it differs from the real consumption by 0.4%. What if Mario is always gone, if I move out for the next year? That will save around 2.9% of gas consumption. That's not enough. I stay at home. If I'm always at home, I would increase gas consumption by 1.7%. I do not really trust that data, honestly, because remember the daily error was plus minus 20%, the average error. If this small change is really true, I'm not sure. But if you wonder why my son can keep his girlfriend, that's why. She does not influence our gas consumption at all. Neither in that direction nor in the other direction, so that's perfectly fine. And what is really very sad, our fireplace has no big influence either. 0.4% is not important. And I'm also surprised that even if my son's girlfriend is leaving and never staying in our house, the gas consumption will go up. That's some statistical change. But what is really important, and all of my models showed the same actually, when the average temperature is 1 degree higher or 1 degree lower, the gas consumption changes by plus minus almost 10%. If the outside temperature changes by 2 degrees, it's plus minus 20%. So climate change is risky. And first I was happy that if the temperature is rising, we use less gas. But then someone told me that the Gulf Stream might collapse and then it's getting really cold. And that would be really bad for the gas consumption. So I'm still afraid of climate change. So the data that I really get from all of these models is limited, but what did I really learn? The presence detection with wireless LAN is very easy to do, very nice, but it's very easy to draw the wrong conclusions from it. I detected that my mother was in our home while we were away, so I confused her, I accused her of burglary, and then we noticed she was just passing by outside. And the mobile phone logs into our wireless router, of course. So I misinterpreted the data. Or my wife had problems with our wireless LAN, so she switched off the wireless LAN in her mobile phone. So she wasn't at home over Christmas. Which is not true. I'm pretty sure she was there. So the data is not really accurate. It was nice, I was really happy about that, but it's not really accurate. About the machine learning, again, it's easy to misinterpret the results. I created a lot of models, and if you fool around with the data, you find a model that is giving exactly the statement that you're looking for. So know your data and understand the statistics if you really want new knowledge from that data. And about the project in general, documentation was really, really important for me to understand this project over the course of a year. Monitor, that's really, but playing is the best way to learn. And if you feel the pain of losing data, or if you feel the joy of creating optical character recognition with a MySQL database, then this is the best way to learn anything at all. So I can only encourage you, look for any kind of project and do the same. It's great fun. Thank you.